Up until this point, when we went to find the derivative of a function, we had to use the limit definition of the derivative, which, to be perfectly honest, was both brutal and tedious, right? There's got to be a faster way. And there is. Secrets to be revealed in this lesson. Our first objective, to derive and use differentiation rules for constant power and polynomial functions. So what used to take you hours to take a derivative is now only going to take you seconds with these shortcuts that we're about to come up with. And objective 2, we're going to do the exact same thing for exponential functions, like this guy right over here. I wonder what the derivative of this function is. Okay, so let's start off with a warm-up activity. Use the limit definition to find the derivative of f of x is equal to c, where c is some sort of real number. So we just have a constant function. It's like y equals 3. I want to find the derivative of that. Well, when you think about it, isn't that just like a horizontal line, right? See, I've got one right here. Whatever that c value is doesn't really matter. If we find its derivative, what's the slope of a horizontal line? It's 0. It should be 0. However, we want to actually show that that is 0 using the limit definition of the derivative. All of these things are going to be traced back to the limit definition of the derivative or anything that was proven using that limit definition. Remember, that's how deductive reasoning works. That was the whole point of you taking geometry. So we'll set it up like this. Just like we've done all of the other derivatives. Wait. I should start off with this. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. And now let's go ahead and plug in x plus h into this function here. So when I plug in x plus h into this function, what spits out is a c. C minus, and then f of x is also c, and then over h. Hey, what's c minus c? I'm pretty sure it's 0. The limit as h goes to 0 of 0 over h. That should be 0. Well, here's one way to think of it. H is not 0 yet. It's just approaching 0 from either side. And we're taking 0 from a number that's getting closer to 0. 0 divided by that number should be equal to 0. All right, well, there's one way to think of it. Another person might look at this and go, you know, if I were to plug in 0 like I'm supposed to, I get the indeterminate form 0 over 0. You know what I mean? Right here. Right, that 0 over 0, and then I have to fix this. Well, you don't have anything to factor or rationalize or anything like that, so maybe we break this up into its left and right side. Just be terribly thorough with this. So the limit as h goes to 0 from the left of 0 over h. Now we know for certain that this is not 0. It's just getting closer to 0. Some number that is close to 0 on the left side of it, just a little bit less, like maybe negative 0.001. Well, 0 divided by negative 0.001 is 0, right? Or negative 0, because we divided by a negative. And then let's do the exact same thing on the right-hand side. The limit as h goes to 0 from the right, 0 over h. And then again, let's choose a number that's just really close to 0, just a little bit bigger. So like positive 0.001. 0 divided by positive 0.001 should be 0. There we go. Or in this case, a positive 0. And since they're both the same, then that means, of course, the limit as h goes to 0 of h over 0 should be equal to, wait a minute, that's not what it was. It was 0 over h. Come on, is equal to 0. Yeah, that was a probably overkill to demonstrate that if f of x is equal to 0, is equal to c, and that could be a 3, a 5, a negative 2, pi, whatever, then f prime of x should be equal to 0. Right? We just used a calculus atom bomb to show that the slope of a horizontal line was in fact 0. Here's that Leibniz notation for the derivative with respect to x of any constant is equal to 0. Again, that constant is some sort of real number. All right, which brings us to the objective for this First part of the lesson, being able to derive and use the differentiation rules for constant, power, and polynomial functions. And we just did the first one. Check, constant rule, the power rule, and the polynomial functions is based on the picture that we have going on here. So if you've ever played this ancient game called Leapfrog, you know what's going on in the picture. And Leapfrog has something to do with the power rule. Now, when we're done with the power rule, we'll also have a constant multiple rule, and we can also do some sum and difference rules. And when we put all of these things together, we'll be able to easily take the derivative of a polynomial function. So speaking of that, we'll start this whole process with an investigation. So here's something that I would want you to do. You stop the video in order to perform this particular investigation. We want to find a general rule for differentiating any power function. Power function looks like a variable raised to a power. X squared, x to the third, and so on. So we have f of x is equal to x to the nth in general. To accomplish this task, you're going to use a combination of inductive reasoning and then the limit definition of the derivative for f of x is equal to x to the n on just these first 5 power functions. Y is equal to x to the first. Well, I don't even need to use the the limit definition on that one. What's the derivative of y is equal to x to the first power? It's just y equals 1. All right, well, I've got that one done for you. And now for the rest of them, we want to use the limit as h goes to 0 of f of x, whoops, let me turn that into a plus sign. There we go, plus h minus f of x, all of that over h. And then let's see if we can establish some sort of pattern here so that we can find the derivative of x to the nth power.